So I'd like to continue talking about the derivative as a function. And in particular, what I would like to look at is when we look at a derivative or when we look at a graph of a function, what can we say about what the derivative should look like? So let's look at graphs of y equals f prime of x versus y equals f of x. Now, the things that we should notice here are intuitively what we kind of expect to have happen is that if we are dealing with a function, if the function, like we sort of look at what does the tangent line look like, and that should help me kind of sketch what is going on with the derivative. For instance, let us suppose that I give you this function. And I say here is y equals f of x. What do I suppose that the derivative should look like? Well, what I can do is I can just think about what does the tangent line seem to be? What is the slope of the tangent line at a given point? So as I come along here it looks to me like I have a relatively large slope on my tangent line. So we're going to have, something fairly big, but it is getting slightly less steep as we go. So this steepness of the tangent line is going to be decreasing here, but the slope is positive, so we get a positive number for our derivative. Now, as we come in towards here, it looks to me like the tangent line is kind of leveling off to be horizontal. So as we pass that horizontal, it's going to cross through 0, and then it starts becoming a downward slope, and it becomes a larger and larger downward slope. So my derivative continues to become a larger and larger negative number. And so here is my y equals f prime of x. And again, I just got this by looking at this curve and asking myself, okay, what does the tangent line's slope appear to be at these different points? Now, here's another example that we could sort of think about that maybe is, well, I don't know if it's simpler, but here's another one. So I'll start by sketching the function. So let's suppose that this is my function. It comes up, it comes down, and then it does this kind of thing. And then it keeps on going like this. So what do I think that the derivative should kind of look like in this situation? Well, the answer is, it starts off with this tangent. It looks basically like a straight line over here. And it's a straight line that has a slope of about 1. So we're going to have a constant slope like so. But then, when we hit this point, we get this corner, and the derivative is going to be undefined. And it swaps over to this negative slope of about -1. So it looks to me like we have this jump in the derivative like so. And it remains about -1 for a while. But then, as we cross this axis, it starts to become steeper and steeper being negative, and it looks to me like we actually end up approaching a vertical tangent here. This is a cusp shape where we get a vertical tangent on both sides. So my derivative will have a vertical asymptote there, and it goes down towards -infinity because this is decreasing, and then we're coming up again, but it's still kind of a vertical asymptote here, or it's still a vertical tangent kind of thing going on here. So this now comes down from +infinity, and it keeps on increasing forever, but the increasing seems to be slowing down. So it looks to me like the derivative should start getting smaller and smaller and should end up having a horizontal asymptote of 0. So there we go. We were able to kind of sketch a little bit of a picture of the derivative here just by looking at a sketch of the function itself. Now, later on, we're going to make precise all of these ideas. We'll be able to say exactly what we mean, and say, okay, if I have this kind of a picture for my function, this is exactly what the derivative will look like. All of these things, the derivative ends up telling us a lot about the shape of the function, and the shape of the function tells us a lot about the derivative. But for now, we're just kind of going intuitively with what this looks like. Let's take a look at some other examples here of functions and then looking at what their derivatives should look like. So let's suppose that this is my function. Maybe I have something that looks like this. Take a minute on your own and see if you can kind of think of the general shape that you think we should have for the derivative of this function, or the graph of the derivative of this function. So I'm going to give you a minute, think about that, and then we'll get back into this. Okay, were you able to come up with something? So it looks to me like as I walk along this curve, I start off with a fairly rapid increase. So it's going to start off being fairly large. And eventually it's going to kind of, as we come down here, as I move over to the right, the tangent is getting less and less steep. And in fact, we get to a horizontal tangent here. So it looks to me like the derivative must come down like this. So it's a big positive number, but then it comes down to 0 when we reach this horizontal tangent. And now we're sort of turned around and we now have a negative tangent for a while. So it's going to be negative, negative, negative. Oh, and then over here it becomes horizontal again. So eventually it must come up like so. And now from here on out we have a positive tangent that seems like it's just keeping on getting bigger and bigger. And so we end up with this kind of a shape for my y equals f prime of x graph. Notice something interesting here. If you look at this, my f of x, this actually looks kind of like a cubic curve. You can think of some cubic polynomials that look sort of this shape. And my derivative looks sort of like a degree 2 curve. It almost looks like a parabola. That is not a coincidence. One of the things that we will see is that the derivative of every cubic turns out to be degree 2. In fact, when you differentiate polynomials, we will see that you always just lower the degree by 1. So this is an example sort of where obviously this doesn't show it, but this definitely illustrates a more general principle that we're going to see in the future here. So here's a bit of a more challenging one, perhaps, to think about. Let's suppose that here is my original curve, and I want to think about what the derivative looks like. So here is my y equals f of x. And again, I want you guys to take a minute and see if you can sort of visualize what the derivatives graph would look like. You can think about what is the slope of the tangent line as you walk along this curve and see what you get. Okay, were you able to figure anything out? So it looks to me like in this case, we start off with a very negative slope. So we're going to be really, really negative, and then it starts to sort of flatten out here. And in fact, somewhere around here, we actually hit a horizontal slope. So the horizontal slope means the derivative should be 0. Then we end up with a positive slope for a while. And then it starts getting smaller again until we reach a slope of 0 again along here. Because here I get a horizontal tangent line again. And then we're going negative. So far we've got a curve that if I start joining up these points, it has sort of this kind of a shape. Then it's negative again for a while, but it comes back up to 0 when we hit this horizontal tangent over here. And then it is increasing and increasing forever. So we just kind of go up like that. Now, once again, you'll notice that f of x, this looks like a 4th degree polynomial almost. It's got 1, 2, 3 local maximums and minimums, And the derivative looks kind of like a cubic shape. Again, not a coincidence. That is something that we will be able to prove later on. It comes back to this fact that when you take the derivative, you lower the degree of the polynomial by 1. Now, of course, you can do this kind of thing when you're talking about stuff that's not just polynomials. You know, the shapes that we've drawn may not have been polynomials. They just sort of looked like polynomials, maybe. So, as another example of this kind of thing, maybe I have something like a thing that looks a little bit like a sine curve of some kind. So we have something that's going up and down, and it keeps on fluctuating back and forth like this. What is this derivative going to look like? Again, why don't you guys take a minute to see if you can come up with the derivative of this curve, which for some reason this time I drew the original curve in blue instead of black, so the derivative is going to be in black this time instead of blue, which is not consistent with what we've been doing, but hopefully you'll be okay with keeping track of which color is which here. Sorry, trying to get my window shut. There we go. Okay, so were you able to figure it out? So it looks to me like the derivative, here we have this positive derivative, but it comes down to 0 as we go through this horizontal tangent. And then it becomes a negative as we come down here, but back to a horizontal tangent when we get to the bottom of one of these waves. And then it's going to go up to a positive. And over here, well, it remains positive, but it comes down to being 0 when this one hits a minimum. And then over here, it's negative. Because remember, we're always thinking about the slope as we go from left to right. So over here, it would be negative, but it comes back up to 0 as we hit this peak. And what does this curve kind of look like to you? Because it looks like a cosine curve. This is my y equals f prime of x, and it really looks a lot like a cosine. It's a sinusoidal wave, but it's shifted so that it has a peak at 0, which is like the cosine curve. This is not a coincidence. Everything I tell you here, nothing is coincidence here. Literally everything we are working with, there are connections that are important that are going on here. In this case, what we will see is that the derivative of sine ends up being cosine. It's a lot of work to prove. We will do it later, but when we see it, intuitively, it will make sense. Because if you think about this as literally a sine curve, so if I think of, here's 1, here's -1, and we'll say this is out of pi, this is out of 2 pi, and so on, well, then it's not maybe obvious exactly where the peaks go, but you can kind of see, yeah, this looks like the derivative should at least be proportional to cosine, if not cosine itself. And so that is exactly what we are going to see here when we actually do the proof. But this intuitively sort of suggests that the derivative of sine x should be at least proportional to the cosine of x. And maybe we need to do a bit of work to think about what that proportionality is. Actually, there's reason to think that the proportionality should be equal to 1. And the reason for that is if you think about sine x or sine theta, sine of theta is the y coordinate in your unit circle. Well, if I start shifting along a certain arc length around here, then I essentially shift my y coordinate by approximately the same amount. So it seems like near 0, the change in my sine per change in my angle should be approximately 1, which would suggest that the derivative should actually equal cosine x. And as I said, we will prove that that is the case later, but we can kind of intuitively see that that is what we would expect here from this example. Now, we don't just have to think about functions that look like normal functions that we work with all the time. We can think about functions that just sort of look like some, arbitrary curve. And we can still draw their derivatives, or at least approximately draw their derivatives. You can't do an exact job, but maybe I have something like this. And this is my y equals f of x. So again, take a minute and see if you can sketch what the derivative would look like from this. So what you can do here is you can say, all right, let's take a look at this thing. Over here, we have a very large positive slope to our curve, but it comes down to 0 when we hit this horizontal. And then we have a very large negative slope, but it comes back to 0 when we hit another horizontal. You'll notice here, by the way, anytime we go through a peak or a trough that is a nice smooth shape, what we really end up with is a horizontal tangent. And again, not a coincidence. Literally nothing we are talking about today is a coincidence. We will come back later and show that whenever you have a peak or a trough, you have to have a tangent of 0, or maybe the tangent line doesn't exist. But if the tangent line exists, it's going to have to be 0. So then we have an increasing slope for a while, but it comes back to being basically a slope of 0 for all of this time, and then it starts increasing again. So the shape that I end up with is going to look like this. It comes down to here, comes down to here, back up to here, over like this, stays around 0 for a while, and then it ends up increasing. And here is my y equals f prime of x curve. So there we go. We end up with a rough sketch of what the derivative would look like based upon this function. Now, the way that you want to check this is you go back and you ask yourself, does this make sense? Does the curve that I'm looking at, is it positive when the slope of my original function is steeply upwards? Is it, a big positive number there? Is it positive but small near places where the tangent is going up to the right, but it's small? You just ask whether it makes sense that way. Then you look at things like, does it go through 0 when we go through a smooth peak or trough where we have a horizontal tangent? So using these kinds of ideas, we can see that there is a close relationship between the shape of the original function and the shape of its derivative. It's not to say that their shapes are the same. They don't have similar shapes. That's not what I'm saying at all. I'm saying that there is a close relationship between them, so that from the graph of the original function, we should be able to kind of sketch what the derivative would look like. Now, you might wonder if it's possible to go in the other direction, and the answer is, yeah, it kind of is. We'll talk about that more later when we talk about antiderivatives. But if you look at the sketch of a derivative of a function, you can kind of guess the overall shape of the original function. Because, if I just look at this blue curve, I know that the original curve must be kind of sloping upwards quite steeply, and then it stops sloping upwards very steeply and switches around to sloping negatively, and then it switches around to sloping positively again. Then for a while, it must remain about constant because its tangent is approximately horizontal, and finally, it must start increasing again. So you can go from a sketch of the derivative and you can say, okay, from this derivative, this is what the original function's shape has got to look like, at least approximately. So there is this close relationship between these two things. Now, what we're going to get to next week is we're going to start in on looking at some rules for how do you actually compute the derivative of a complicated function without having to go back to using the limit. In other words, how do we find that derivative without having to explicitly work with the limit definition? So that's what we'll be starting up with next week. the meantime, let me know if you have any questions.